Oh, yeah, that's right. Frequency.
You were correct, frequency. All right, so yeah, so as we talked about, we know the fact that if a wave is very, very big, the number of waves that'll pass by a spot in 1 second time will be very little. That's frequency. If a wave is very little, the number of waves that pass by a spot at the same time would be really, really big. That's also frequency. Speaking of frequency, that V, that special V, is known as nu and U, but this is going to be frequency. And I'm color coding it as purple. And the unit for frequency is the per second, as you may recall. We also have this upside down Y, which is lambda, but that's really our wavelength. And that's usually in the problem, it has to be in meters, yes. You don't have to, but I recommend it. And then the new thing today is this C, and the C is a constant. And for those of you that may have taken physical science at some point in your career, you may recall that there was a constant in physical science that we used often called gravity. And gravity had a value that said that anytime you drop anything, it falls at a rate of 9.8 meters per second towards Earth, right? So every time that you use gravity in a formula, it was always 9.8. And every time that you use C in a chemistry formula, it's going to be the speed of light constant. Okay, and the speed of light constant has a value of 3.00 times 10 to the 8 meters per second. Okay. Now, anytime you see C, that's what number you have to report or use. You do not have to memorize the speed of light constant. It will be given to you. You do not have to memorize the formula. It'll be given to you. You just have to know how to use it. So let's take a second and practice it. But before we do, I'm going to refresh your memory on the diagram that we spent a lot of time looking at yesterday. The diagram that we spent a lot of time looking at yesterday was the electromagnetic radiation spectrum, where on the top you had wavelength in nanometers, and on the bottom you had frequency in per seconds. Does that sound vaguely familiar? If it doesn't, here it is. Okay. We will use this to help us to determine what type of wave we are calculating as we go through. So, problem number 1, and here's how I'm going to do this. Calculate the wavelength in nanometers. I generally highlight or underline things that are important in the problem. So the wavelength in nanometers of electromagnetic radiation that has a frequency of 6.54 times 10 to the 17 per seconds. Okay. Now, in this problem, I know that I'm going to be using the formula C is equal to wavelength times frequency. Okay. And I'm going to take the time to identify my variables off to the side, because sometimes it's easier to see when they're all in the same spot. And let's be real, nobody likes to read math problems. Now, in this problem, the number that has been given to me is 6.54 times 10 to the 17th per seconds. The problem is asking me to calculate the wavelength. I know because I've been given C. C is always going to be 3.00 times 10 to the 8 meters per second. So now the next thing I'm going to do is I'm going to substitute the numbers that I have into my formula. So it's going to be 3.00 times 10 to the 8 meters per second will be equal to lambda, or wavelength, times 6.54 times 10 to the 17th per seconds. Now, what math do I have to do here? Multiply, divide, add, or subtract? Yeah, I'm going to divide. So I'm going to take and divide both sides by the 6.54. Like so. And when I grab my handy dandy calculator, and if you don't have a calculator at your desk, there's some randomly scattered about the room, and I highly suggest you use a calculator. There's one right back there. Right there. Okay. When you're putting numbers in scientific notation into the calculator, what's the trick?
Oh, E.
You got to use the E, right? So everybody wake up your calculator. Good afternoon, calculator. Hope you had a good nap. And let's plug this in the calculator and see if we get the right answer.
What do we do for that second?
Pardon?
What do we do for the second? Or do we do nothing? Seconds.
You would just take the 3.00 times 10 to the 8 divided by the 6.54 times 10 to the minus 7, or times 10 to the 17. That's it.
Oh, that's just.
Okay. Yeah. Okay. So I got 4.587155596 times 10 to the minus 10. If you got the same number, but like times 10 to the minus like 26 or something like that, or 25 or something like that, it means you put this in the calculator incorrectly. Okay? Does anybody need help with their calculator?
I got like 16. Like to the 16.
Well, let me be right back there and take a look-see. All right, sig figs. Now, how many sig figs does 3.00 have? Yes, I agree with that. Thank you.
Same with 6.5.
So this one has 3 sig figs. Please come back. 3 sig figs. So my answer has to have 3 sig figs. So I'm going to 1, 2, 3. That 7 will round that 8 up to a 9er. So my number here is going to be 4.59 times 10 to the negative 10. Now, what unit will I have? Will it be meters per second? Will it be meters? Will it be per seconds? Will it be nanometers?
Meters per second.
Nanometers? Because it's wavelength.
Why is it not meters?
It's going to actually be meters
Meters. My bad. It's just meters.
because the per seconds would cancel out. Now, here's the shoot, I did that in the wrong color. So here's the problem. 4.59 times 10 to the negative 10, and that's going to be meters. There, okay.
It says calculate the wavelength.
You are correct. He said it says calculate the wavelength in nanometers. So the issue is because the formula, in order to do the formula, it has to be in meters. We now need to do one extra step, which is convert meters to nanometers. And if you may or may not remember from a million years ago, 1 meter is equal to 1.0 times 10 to the 9th nanometers. So now what I'm going to do is I'm going to take my 4.59 times 10 to the minus 10 nanometers, and I'm going to convert it to meters. And when I convert it to meters, what unit should I put on the bottom? Oh, wait. Slow down, V. Yep, slow down.
No, wait, you put meters on the bottom.
Meters. Okay, yeah. So, if I want to get rid of meters, I need to put meters on the bottom. So I'm going to put 1 meter on the bottom. And I'm going to put 1.0 times 10 to the 9 nanometers on the top. I'm going to use my calculator, multiply it times 1.0 times 10 to the 9, and I get a value for my wavelength to be 0.459 nanometers is my wavelength. It's not, it's just a lot of steps. It's not imaginary numbers. All right, now, the other question that it says on here is what type of electromagnetic radiation is it? And in my case, what I think would be the easiest way to do it would be to use a number that was given to me in the problem. And the number that was given to me in the problem was the frequency of 6.54 times 10 to the 17. So I'm going to go back up here and I'm going to look for 6.54 times 10 to the 17, which would be right here. Oh, I should do that purple. You are correct. So that tells me that this type of radiation, or not radiation, this type of, it is, electromagnetic radiation is an X-ray. Checking out your bones. Yes?
Okay, so see how our answer was like 4.59 and then we did all the the other thing and we got 0.459. Can you just always move the decimal over instead of doing all that? Or will it be different?
Oh, yeah.
It depends. So it won't always be times 10 to the minus 10. And so like in this case, because the original number was times 10 to the minus 10 and the conversion was 10 to the 9, we moved it 9 places, the decimal 9 places. So like in theory, you can move the decimal X number of places, but it won't always be just simply pushing it over one spot. Okay. Does that answer your question? All right. Next one. It says calculate the frequency, and again, I'm going to highlight what I know, that has a wavelength of 650 nanometers. Okay? So then I'm going to, because we're still using that formula, C is equal to wavelength times frequency. I'm going to again identify my variables. And this time, the only number that's been given to me in the problem is 650 with a decimal point nanometers. My constant, right, is the speed of light constant, which is 3.00 times 10 to the 8 meters per second.
What is the dot after 650?
So in the problem, right, it says it's 650 with a decimal point. So that tells you the number of significant figures this problem has, or this number has, which would be how many?
Why wouldn't they put a 0?
The question is, why wouldn't they be like 650.0? The answer to that question, the actual answer to that question is that, technically speaking, whatever measuring device they used was only accurate to the ones place. So like you can't just add zeros because it makes you feel better. You know what I mean? Like you can't just eat that extra donut because it makes you feel better because you'll regret it later. You know what I'm talking about? All right. Anyway, so looking at my problem here, right? I'm going to plug in what I have, which is 3.00 times 10 to the 8 meters per second equals 650 with a decimal point nanometers times frequency. Now, wait a minute. Can I do this problem the way that I've written it?
No. Well, yes.
Why not?
Because it's nanometers, not meters.
Good. the wavelength has to be in meters, okay? So we have to change it to meters. So what I'm going to do is I'm going to remember that I have 1 meter is equal to 1.0 times 10 to the 9 nanometers. And so I'm going to convert that. And when I convert that, am I going to put nanometers on top or on the bottom this time?
On the bottom.
On the bottom. So I'm going to put the 1.0 times 10 to the 9 nanometers and the 1 meter on top. I'm going to grab my calculator, take 650 divided by 1 times 10 to the 9, and I get a value for my wavelength this time to be 6.50 times 10 to the negative 7 meters. Now, I wrote this out, and I'm going to leave it in there, but I'm going to cross it out just so that hopefully when you're doing these problems on your own, you can be like, oh, wait, I got to change this. So I'm going to rewrite it real quick once. 3.00 times 10 to the 8 meters per second. Now I'm going to use the correct converted value, which is 6.50 times 10 to the negative 7 meters, which will give me my frequency. And again, I'm going to divide. So I'm going to divide both sides by the wavelength. Like so. And use my calculator. 3 times 10 to the 8 divided by 6.50 times 10 to the negative 7. And the calculator is going to give me a frequency value of 4.61538, times 10 to the 14th. What unit will this be?
Seconds.
Per second,
First whole.
right? Because it's technically on the bottom. Again, we have to assess significant figures. So the given value in the problem had 3 sig figs. So this number has to have 3 sig figs. So that 5 will round that 1 up. So my final answer will be 4.62 times 10 to the 14 per seconds equals frequency. Now, in this instance, I still have to figure out what type of electromagnetic radiation is. And I can use one of two things. I can either use the frequency that I just calculated or the wavelength that I was given. And I usually like to use the number that I was given in the problem because that's what the measurement was originally. So it's 650 nanometers. So I'm going to go up here and I'm going to locate 650 nanometers, which is then this general region right here. So that you could argue that it's red, but really in reality, we're just going to say that it's visible light spectrum. So the answer for what type of EMR is this is visible light. Okay. Questions about this one?